will not introduce you guys. You can do it by your own. So because you have many things to say about yourself, about it. So I don't want to make mistakes. Okay. I just put the moderation chat. Just me 1 second. The moderation chat. And then it's up to you guys. So go ahead, please introduce yourself, and just the show is yours. Okay.
All right. Well, thank you for that introduction. Hello, everyone. My name is Chris Serrano. I'm with SICK Product and Competence Center of the Americas. I'm based in Cleveland, Ohio, and I'm the Safety Standards and Competence Manager for SICK, responsible for competence and standardization efforts across the Americas and for all of SICK. Aaron, you want to go ahead and introduce yourself before we jump in?
Yeah, absolutely. I'm Aaron Weike. I am also based in the U.S. out of the Minnesota headquarters for SICK. I'm a product manager looking after some of our safety products within our serial product portfolio.
All right. Well, with that, we'll just go ahead and jump right in. Today's presentation, we're talking about scalable safety solutions for mobile platforms. We tried to kind of break it down into some bite-sized pieces for what we're going to talk about. Aaron and I are going to kind of tag team this, where I'll take the first half and Aaron will kind of fill in on the back half, so we can try to give you as complete a picture as possible, knowing that we only have an hour and we're going to try to cover as much as possible. So starting, we have to understand what it is. What is the problem statement? What is it that we're trying to do? And of course, what we want to achieve as best as possible is safety and productivity to go hand in hand. For too long, people would focus on one or the other, and usually at the expense of the other. And what we're really trying to do as we move forward, especially in today's environment, is for safety and productivity to go hand in hand and to be able to complement each other as opposed to conflict with each other. So when we talk about safe productivity, we have to understand that mobile platforms are being adopted at unprecedented rates, especially over the last year and a half with the pandemic. And this is happening both in factory automation as well as logistics automation. As more and more of these platforms are introduced into the workplace, of course, there's going to be more human interaction to be expected. And so what we want to do is implement these applications safely. And that's a requirement, right? It's a requirement of regulation, of standards, of our culture today. And we want to make sure that it's safe, but at the same time, keep those levels of productivity as high as possible. So when we talk about a mobile platform, what exactly are we talking about? These things go by many different names. There's probably even more than what's listed here. As we talk about safety, obviously there's going to be standards that apply to these either domestically or internationally. These are just a handful of the ones that we're going to talk about and where some of these terms apply or appear. At the end of the day, we're talking about a unit that is ground-based. So right now we're omitting water-based or air-based mobility. So it's based on ground, typically wheels, but not exclusively, and platforms that move around for logistics or factory automation influences and increases. So the misconception that we're trying to address here today is this idea that when we talk industrial safety and we talk mobile platforms, that the performance level or the PL always has to be a performance level D. Or if we're talking safety integrity levels, that it always has to be a SIL 2. This is a misconception that we do want to try to clarify here to start off this conversation. So we know when mobile platforms are deployed, there's not just the consideration of the manufacturer who's putting the machine on the shelf with a part number for people to buy and use it, but there's site-specific customizations, there's application requirements that makes each and every deployment unique. So to take this approach where we think that a one-size-fits-all is going to work for all of those customized applications is a bit misleading, right? For one, we know there's different shapes and sizes of mobile platforms that are out there. Their uses are unique. So this is really what's driving us to evaluate this misconception. Is a one-size-fit-all approach really practical? Is it reasonable? Is it feasible? Is it necessary? So when we look at this and we raise this question, we should start to think about some of the tools that are available to help us evaluate this. And one of the best tools out there is the risk assessment approach. So with risk assessment, we evaluate the inherent risk of the application and then design a risk reduction strategy commensurate to that level of risk. So when we talk about mobile platforms, the obvious thing to look at, one of the obvious things, is to look at the mass. It's not only the payload, but the mass of the unit itself. Obviously, with more mass, there's more force, which means a higher severity. With lower mass, there's lower force and potentially less severity. When we look at the speed of the unit, we need to consider that as well. Speed, interestingly enough, has an exponential factor on risk. With lower speeds, not only does it carry less force, but it also increases the probability of avoidance. Whereas faster moving vehicles, even if you see them, if they're moving too fast, you may not be able to get out of the way. So at a very basic level, the small, slow mobile platforms are typically have less inherent risk than the large, heavy ones that are moving quickly. But another thing that we have to consider here are the people that are exposed. If we're talking about trained employees in a factory environment where there's controlled access and the affected people have a certain level of training, there's going to be a different level of risk than if we have John Q. Public exposed to the mobile platforms operating in the environment. So this too is going to affect risk specifically with the probability factor. So based on these criteria, as well as others during the risk assessment, we can evaluate each application and come up with a custom fit solution, one that's appropriate, that's adequate, that meets the requirements of the demand on the safety system. So when we start to take this approach, I can't help but think about the Goldilocks principle. Those of you familiar with the children's story, the three bears, Goldilocks finds her way into the house of the three bears, and as she starts to see what they have, their bed, their food, she sees that usually there's one that's too much extreme one level, there's another in the opposite extreme that's not enough, and somewhere in the middle there's something that's just right. And what we want to try to do is apply this, right? Goldilocks had it right. Why do we have to settle for something that's too much in one extreme or the other, especially when we have alternatives that are now available with cutting edge technology and methodologies? So as we apply this Goldilocks principle to industrial safety, the best way to do this, to take the subjectivity out of this, is to base it on a risk assessment. Evaluate the risk. Depending on the level of risk, will determine where those thresholds are of just right. So that leads us then into the next step, which is how do we fix this misconception, and how do we gain clarity by utilizing the risk assessment process as it's been defined for 30 plus years. So let's start, for any novices out there, what exactly is risk? Risk is when you have a hazard and you have a person and they're in the same place at the same time. This leads to a potential for harm. That harm can be evaluated based on the level of severity and the level of probability. And when we estimate those together, we can define risk. We can estimate risk that can then be evaluated. In order to estimate that risk, we have to understand that the hazard is going to have a direct effect on the hazard consequence, which defines the level of severity. And we always take a worst credible possible case. And then when we look at probability, this is most often dictated by the person, typically by their task. It could include their level of training and understanding. But these two things together help us quantifiably estimate severity and probability, which in turn then gives us a level of risk, a risk that we can measure, we can evaluate, and we can determine if it's acceptable or not. So that then leads us into what is acceptable risk. It sounds very subjective. It's defined as shown on the screen here. It's at least in accordance with legal requirements, and it takes into consideration state of the art. Still seems a little vague to some people, but essentially, to simplify this, we know risk is on a scale. There's low risk and there's high risk. Typically, when we do our initial risk estimation, we consider no risk reduction measures in place, and we have the inherent risk of the application, and we want to reduce that to some level that's acceptable. Acceptable doesn't necessarily mean zero risk. In reality, zero risk isn't necessarily attainable, although it's a great goal that we want to work towards. But we need to take this initial level of risk and reduce it to a level that's acceptable. And that acceptance is depending on the environment and the application. Here we see just a really simplified approach. What's acceptable risk to an adult is probably not acceptable risk for children, right? If we're working at height, adults can work with a simple handrail that meets certain requirements, whereas children that could fit through those handrails, intentionally or unintentionally, need to have a higher degree of risk reduction in place. Whereas if we have a task like cleaning windows, obviously there has to be a different level of acceptance. Or people recreationally or otherwise that are free climbing, there's acceptance of risk is somewhat subjective, but we need to make it repeatable and as definable as possible so that we get to meet the legal requirements and we consider what's current and state of the art. And then we apply risk reduction measures to get us from that inherent level of risk to that acceptable level of risk. So how do we estimate the risk? As I said before, risk, as it relates to an identified hazard, is a combination of the severity of the possible harm as well as the probability of occurrence of that harm. If we look closer, probability can be defined a little bit more granularly. We can look at frequency and duration of the exposure. We can look at possibility of avoiding or limiting the harm. And we can also look at probability of occurrence of a hazardous event. As we start defining it more succinctly like this, we get these risk parameters or these elements of risk that we can then objectively define and grade on a scale. So if we look at an overview of the process of risk assessment, safety level, the performance needs to be commensurate to the level of risk. So if we agree that risk is on a scale, then we want to have safety systems that perform according to that degree of risk. So we can statistically define this as a probability of danger to failure per hour. So what this really means is the more dangerous something is, the lower the probability should be that it's going to fail to a dangerous condition. And these can be statistically, mathematically modeled. If we look at standards that are available out there internationally, we have ISO 13849 defines these as performance levels and assigns labels to them. If we look at IAC 62061, it calls it safety integrity levels, assigns different levels, but it's still the same thresholds, if you will, that define the performance commensurate to the level of risk. So if we take then the risk assessment process, if we look at severity and probability, you see at the top of the scale, the lower severity and probability gives a lower level of risk, which means that the performance doesn't need to be nearly as reliable as elements at the opposite end. So what this tells us is when we do our risk assessment, we're going to define some level of risk. We can then assign thresholds to that. And depending on what model or standard we want to use, in this example, I'm using 13849, we can then assign required performance level. That's the PLR. What's the performance level required for any solution for that task hazard pair? And then we can subsequently select the right risk reduction measures, the right technologies, and the right solutions that meet or exceed those requirements. So if we take a really simplified approach to risk assessment at a high level, first thing we do is we identify applicable laws, regulations, and standards, depending on the industry, depending on the region of the world. We then perform the risk assessment, which we'll go into here in a little bit. After the risk assessment, if the risk is not acceptable, then we apply risk reduction. That's done in a three-step method. We start with design measures, inherently safe by design measures. We then talk about engineering controls, guards and devices, and complementary measures. And then last but not least, the information for use. After those are applied, we perform overall validation of the system to make sure that it's meeting the expectations of the functional specification. And then the machine can be released for use. So at this point, there's going to be a quick call to action. Hopefully, Alfredo can put this up on the screen for you. We have a link to another document. It's 200 plus pages that goes into great detail on this 6-step process. That's not the point of what we're here for today. So I just want to reference it, let you know that it's available to you if you want to go look at it. So following this simplified approach, we do our initial risk assessment, again, assuming that there's no measures in place. We define an inherent risk, or the risk in. And historically, what people would do is they'd apply all their risk reduction measures all at once. Then, they'd apply those measures. They would evaluate the residual risk and the risk out. And if that was acceptable, they'd document it and they would be done. This is a very, very simplified and common approach to risk assessment. What's the inherent risk? What are you going to do about it? And what's the residual risk? And as long as that residual risk is acceptable, everything is fine. When we talk about an iterative approach, they're still using the exact same model. This is out of ISO 12100, a very well-known risk assessment document, guidance on doing risk assessment and risk reduction. We evaluate the initial risk in. We then consider what are the step 1 measures that can be applied. And based on their proper application, we evaluate the residual risk, the risk out after step 1. And if that's not acceptable, then we continue through the process of risk reduction. We go to step 2. And here we see the residual risk after step 1 is now the remaining risk coming into step 2. And we apply our step 2 measures, our guards, our devices, our complementary measures, and we evaluate the residual risk after that. And if that's not acceptable, then we continue on to step 3, where again, the risk out after the previous step is the risk in for the subsequent step. And so what this shows us is that we can iterate through this model. That's what the model says to do, actually, is to iterate and continue to reduce the risk step by step until you get to a residual risk that's acceptable. And not only does it say to go through it, what step 1, step 2, step 3, but we can iterate within each step multiple times. We want to exhaust each of those levels of risk reduction as many times as possible before we go to the next step. So if we apply this to a real life application, here we have a person that's manually stocking shelves, and we want to replace that. We want to automate that process with a mobile platform that's going to come in and it's going to automatically stock shelves for us. So we need to do the risk assessment on this. We also need to consider it's not just the operator who's an assigned task, but we have to consider passersby as affected personnel as well. So if we look at this approach, first thing we do is identify the hazards. In the US, we usually talk about a task-based risk assessment where we look at both tasks and hazards together. So the first one, the first two, obviously, we have the passerby as well as the worker. Passerby is just in the general vicinity doing something unrelated to the application, whereas the worker's doing an assigned task. And of course, there's risk to both of them. There's a potential harm, severity of harm. To the passerby, it could be being just collision in open space, whereas with the worker, it could be crushing against a fixed element like the shelf. We also have to consider other applications, other aspects of the operation. Here we have a scissor lift that goes up and down. If there's setting or maintenance that's required, there's potential crushing hazards that occur here. And then we also have to consider maintenance, changing the battery or doing other work that there's potential exposure to live parts. This is a very simplified approach. There'd be many, many more task hazard pairs, but I'm just looking at 4 individual ones here in this example. So once we've identified those hazards, we then need to estimate the risk. There's many, many risk assessment or risk estimation models out there. I'm simply using this one for its convenience and its ease of use. There's many that are available that will do the job if they're applied correctly. So what we do here is we look at each task hazard pair and we evaluate the risk. The first one with the passerby being hit, the severity is high, the frequency is high, although the probability might be lower because the frequency of passerbys in the area is not necessarily as high. This puts us at a certain level on the scale of risk, which defines what the performance is for any safety-related parts of the control system. If we look at the next one, the operator being crushed by the mobile platform, here the severity might be lower because of the speed or mass of the application, but the frequency is high. The probability we could probably rate as low. And here we have a different level of risk. If I look at the third one with the crushing, here we have high severity, We also have high frequency and high probability because of how quickly it moves and the force that's generated by the scissor lift. And then last but not least, the maintenance exposure to the electrical hazards. Here the severity is high, but the frequency and probability are both low. So we can see that 4 distinct task hazard pairs have 4 distinct levels of risk in this quick evaluation. So next thing we need to do is evaluate if that risk is acceptable or not, right? If it is, we don't need to do anything about it, but we need to make a determination about whether or not it's acceptable or not. So if we look through these, the first one, we know we can also use the risk performance requirements to help us evaluate. In this example, we said that there was relatively high risk of a passerby being hit by the mobile platform. And if we have control solutions, they need to meet a performance level D. We can easily evaluate the existing platform to see if it meets or exceeds that threshold. As it's shown here, this mobile platform doesn't have anything on it, so that risk is not acceptable. We can do the same for the operator being crushed and see that there's insufficient measures in place to achieve acceptable risk. Same thing with the crushing hazard right now. It's like an exposed moving component where fingers can be, or hands can be sheared or crushed. That's not acceptable. And we can look at the maintenance task. Here, the risk is relatively low. Some people might say that it's acceptable risk. Typically, we're going to say that there's clearly additional measures that can be applied to reduce that risk to a level that's as low as reasonably practicable. ALARP is the acronym. So if we look at this and we apply in an iterative approach our risk reduction measures, we first consider, are there any step 1 measures we can do to eliminate the hazard? And if not, then we go to step 1 measures that are inherently safe by design. Well, one thing we could do is we could put, we could modify the force inflicted by the scissor lift through inherently safe drive systems. We evaluate that residual risk, say, is that acceptable or not, in which case it's not. We evaluate, are there any other step 1 measures? In this scenario, we don't have any. So we continue on to step 2. Step 2, we look at all these individual risks. In some cases, we can apply guards. We can apply monitoring systems to reduce the speed. We evaluate the residual risk to determine is that sufficient or not. And if not, we continue on through the process. We continue to look again at step 2. Are there other measures? Maybe we can use sensors to detect the presence of a person in the path of the mobile platform. We again evaluate the residual risk, determine if that's acceptable or not. And if not, then we continue to evaluate step 2 measures. Are there ways that we can stop or control the energy, whether it's an emergency stop or an energy isolating device? We again continue this process iteratively. We go through, determine is there anything else in step 2 that can be applied? In this case, not. So then we go on to step 3, the information for use. We can apply awareness signals. We again evaluate that residual risk. You see a common theme here. Determine is there more that can be done. We can put up awareness barriers. We can use awareness signs. We can use lockout procedures. We again go through this evaluation iteratively after each step. We go to the next step. We can document instructions for use, information for use, how to operate and perform each of those tasks safely. We can then train our employees on safe work procedures and perform that subsequent risk estimation, risk evaluation. And lastly, we can apply training. So here we see multiple layers being applied of risk reduction measures to each of these task hazard pairs to reduce risk. And what we did is we iterated through each of those steps as many times as we could until we got to a point where we think the final risk out is going to be acceptable. And so this is where we need to now evaluate, what do we do? How do we do this correctly? So using this oversimplified example, let's look at these 4 task hazard pairs. The first one we'll exclude is the one where there is no safety related part of the control system. It's just not interesting for today's discussion. We can also exclude the one where the only control element is the emergency stop. And that leaves us with the final 2. We look at the first one, the top one. This says that with the initial risk assessment, when we have no step one measures, we get to step two, that the performance level for each of these is performance level B. That's a pretty low threshold, pretty easy to accomplish. So let's maybe not focus on that one. Let's look at this last one remaining. We have the passerby being hit by the moving mobile platform. Here, if we were to apply the simplified approach, it says that everything we do in the control system has to meet a performance level D. And this is interesting because this is where we can stop and do a more critical evaluation. Is that really necessary for all the safety-related parts of the control system for each individual safety function? Not only that, but is it practical? And equally as important is that cost-effective? So if we look at this specific one and apply the iterative approach, we start by evaluating the risk, right? Like we did before. We're questioning if PLD is really required. So our initial risk, as we said earlier, severity was high, frequency was high, probability was high. We have no step one measures. So we go to step two. This is where performance level is applied. This says the required performance level for the first measure applied is performance level D. The first risk reduction measure we're applying is performing the safety function of speed limiting through monitoring features. And we have to look, what is the achieved performance level? So what can we achieve? And we compare that to what's required. Are we equal to or greater than that requirement? And if we are, which is possible to do with appropriate devices and control systems, we can say, yes, we've met the requirement of that safety function, but what's the residual risk? The risk out here, we've reduced the severity because we now are monitoring and limiting the speed of the platform. The frequency of the exposure hasn't changed. The probability of occurrence hasn't changed. So we need to determine, is this as low as reasonably practicable? Is this acceptable residual risk? It's probably not. So this means we need to start iterating. So now that we have a risk out after our first measure, we go to our next measure, use those same criteria, those same risk factors now, and that becomes our risk in, which according to this model tells us that the performance level for anything, minimum performance level for anything subsequent is performance level B. Well, here we're going to apply multiple sensors, probably one on the front, one in the back. For personnel detection, here the minimum performance is level B. We could get to level B, we could do level C, level D. Aaron will talk to us more about that later. As long as we meet that minimum requirement or exceed it, we've started to do our due diligence, and now we can evaluate the risk out. Here now we've reduced the frequency of exposure because we're detecting when somebody is in front or behind in the path of travel of a mobile platform. But is that enough? Probably not. So now we take that risk out. It becomes our risk in for our next layer. This now tells us our minimum performance is level A. Here we're going to apply the emergency stop devices, which is stopping in case of an emergency. Performance level A is a really low threshold. There might be other requirements that dictate a higher level. It could be a specific standard or a specific regulation. But as long as we meet or exceed that minimum requirement, we're good. So now we've reduced the severity, we've reduced the frequency, the probability we couldn't reduce any further than it was in this model. But is that still enough? You could say that from the control system side, it looks pretty good, but are there other measures that are practicable that we can apply to reduce this even further? So we're not talking about step two anymore. In this specific methodology, it's not as granular as some others that show us a distinct return on investment for the risk reduction measures. So we're not going to use that model anymore, but we'll say there's still more risk that can be reduced. There's no performance level required because we're not in step two. And we start looking at our subsequent risk reduction measures. We have indications and alarms. Again, no performance level. It's hard to calculate using that methodology specifically what the risk out is, but is there more that can be done? Yes, there is. We go through this one last step. We look at the administrative elements, the training, the safe work procedures, the documentation, the information for use, and determine, has this reduced the risk as low as reasonably practicable? And what we see here is that iteratively, as we continue to apply different measures, each with its own safety function, we can evaluate what the required performance is based on the risk at that moment in the process. So if we jump then to an example of a mobile platform standard. Here I'm looking at the new ANSI RIA R1508 standard for industrial mobile robots. Here we see that there's mandatory safety functions. At a minimum, each industrial mobile robot has to have a stopping function, so the braking function. It has to have velocity limiting, as we discussed previously. It needs to have some type of collision avoidance, typically done with some type of sensing technology. And of course, there's many types out there. All of these tie into the safety control system, so it's safety-related parts of the control system, and we need to have it meet the minimum performance requirements based on the risk assessment. This standard also says there's optional safety functions. Emergency stop, it's optional according to the standard. In our risk assessment, in our example, we said we were going to apply them. Muting is another safety function that could be potentially applied, especially when you have mobile platforms going into docks or workstations where they need to interact with fixed structures. And for a temporary limited amount of time, you want to disable the sensing function, but other safety functions are applicable. Sometimes warning systems in and of themselves are a safety function. Navigation, a lot of times navigation is not used as a safety function, but we're starting to see more and more where the navigation in and of itself is safety relevant and therefore has safety requirements. And then the last one is a stow position, especially if we have a manipulator on top with the arm sticking out as it approaches a doorway. It needs to tuck into a stow position to make sure it clears the area safely. These are all optional safety functions. What's equally important and interesting in the standard is the very next clause, which talks about the performance requirements. Here, it clearly states that the performance of the safety-related parts of the control system are dictated by the results of the risk assessment. And not only that, that the criteria applied has to be documented for each individual safety function. So the days of saying the risk in was this, we're going to throw a bunch of stuff at it, and the risk out hopefully is good enough. This is actually adding the requirement for the specificity. Identify every safety function, design the safety function to the risk, and document the process, which is what we just went through. So now we start to get to what is the secret that we're trying to reveal here today. It's that we're trying to marry this idea of achieving acceptable risk with compliance with relevant regulations and standards to find the just right area, the Goldilocks approach. This isn't to say that one approach that the simplified approach is wrong. It certainly has its trade-offs. It's much easier to apply. We also risk over designing for the application. When we over design, we add complexity, we add cost, and we sometimes affect usability and productivity. So either approach, the simplified approach or the iterative approach, are adequate. They're both usable. They both can be justified through standardization. And it's up to machine builders, machine integrators, and machine users to determine which is the one that makes the most sense for them. So at this point, I'm going to hand the ball over to my friend Aaron. I'm going to stop sharing and ask Aaron to share his screen and let him take it from here.
Wonderful. Thanks, Chris. I'm going to go into presentation mode. So picking up where Chris left off, we want to talk benefits of finding the right safety solution and looking at SICK a little bit more and how we can do that effectively. Our end goal is achieving safe productivity. If you combine the two words, we need the safety, but we don't want safety to limit productivity in general. So achieving safe productivity with scalable solutions and a scalable iterative approach requires solutions to find balance between cost effectiveness, compactness, accuracy, robustness, a whole bunch of other parameters as well. From a SICK standpoint, SICK is a one-stop shop for scalable solutions. So whether you're looking for a one-off safety product like a safety laser scanner or safety controller, we've got safety products that apply to that. There's also safety systems that are ultimately a prepackaged system that combines different products and technology to get a complete system put together. And then we offer safety services ranging from training and education on applicable standards or risk assessment to turnkey solutions, coming in and doing risk assessment and putting a concept together, and ultimately all the way through to verification and validation. So SICK is able to find the solution that's just right for the specific application. And so if we dive into those solutions, we want to look at a couple factors to consider as you're looking at that. A huge benefit to all these solutions is that there's rarely ever one correct or one right solution. And so it's great news, but now the challenge is getting creative to find the one that's just right. And so things that come into question that you want to consider are productivity, connectivity, and total cost of ownership. So we're going to dive into those a little bit more in depth here. So starting with productivity, maintaining productivity is critical. We all know that safety being applied over engineering is going to kill productivity. So we need to maintain productivity on these mobile platforms, but how is it done effectively when you add those safety devices? Just in general, a mobile platform's productivity is based on how well it can perform. This is based on speed of the platform, turning capabilities, and load size. These topics, among others, play into the productivity within normal operation. Historically, if you look at everything over the last 30 years, as we've worked to develop some of these standards and guidelines, safety has been perceived as a hindrance to productivity, like I mentioned earlier. So it's either been simplified or minimized, like Chris mentioned before, or completely overlooked. But when considering scalable safety, a safe vehicle may no longer be a stopped vehicle. So if you look at the image on the right, a safety laser scanner can monitor protected fields that would send stop signals to this mobile platform if an object is detected. So you can turn left, turn right, speed up, slow down, and adjust the speed of the vehicle accordingly based on what the optical device is seeing. In addition, if a protective field is able to switch, like I mentioned earlier, you can slow down more effectively. You can course correct using some of the navigation data that Chris was talking about before. Ultimately, reducing the risk to personnel, and then reducing any machine damage that may happen as well. So another thing from a productivity that you'll want to consider is environmental factors. So more and more we're seeing vehicles and mobile platforms work in the areas of welding applications or dusty and dirty environments, or even outdoor, going from plant A to plant B within the same campus. All of these have their unique challenges when it comes to optical safety devices. So how can these effects be minimized so that we're not seeing nuisance trips in normal operation? So one example of how to do this effectively is with our safety laser scanners, Microscan 3, and you can see the orange one, the outdoor scan 3. They have safe HDDM technology, which helps filter ambient light, dust, or other common nuisance tripping causes, which leads to a lot of downtime normally. So in addition, these safety devices offer other configuration options that allow additional filtering of common nuisance trips, which will drastically improve the productivity of vehicles. So maintaining productivity is critical and shouldn't have to suffer with the safety devices being added to it. So next, we're going to jump into connectivity and look at how connected devices need to be considered with scalable solutions. Safety devices are widely connected. You look at the controls architecture in these applications now. Safety devices can be connected in different forms. It could be Ethernet, CAN, a whole bunch of different field bus protocols that allow communication from safety devices to the mobile platform. And by using this, you can enable other functions coming from, say, a safety laser scanner or safety control system. One example of this additional functionality is measurement data that comes from these devices. So if we consider measurement data, let's look at how it can be used. So again, I'm going to use a Microscan 3 as an example. And if it's connected via Ethernet, this measurement data can be used a couple different ways. First, it could be navigation data. So depending on how much precision is needed, different scanner devices may provide more or less flexibility based on the resolution of the device. But from an application standpoint, if you use a safety device, not only for safety, but also for navigation, you can use this precise navigation data to allow higher speeds of the vehicle and just take guesswork out of where objects are. So as you're navigating through the plant, you can see another small AGV coming your way, or you can see someone walking. You can slow the vehicle down and use this navigational data to find another reference point and move to a safe path on the way from A to B. Second use of measurement data is field switching. So like we mentioned before with safety laser scanners, you may be able to adjust the protective fields being monitored based on different speeds or different direction of a wheel angle, for example. And so a great use case for field switching when a mobile platform is let's look at docking, when it's ready to dock for charging. You can use reference points from a scanner that would allow the vehicle to have the scanner fields reduce or switch and slow down the vehicle so that when you're moving into the dock, it can be done a lot more automatic rather than having someone come by and help it into a dock situation. Next, we want to look at when a device is connected to larger enterprise systems. So you're still communicating Ethernet or CAN or other ways to the system. Few ways you can use this data is for asset ID tracking. So if you look at your plant in general, historically we don't know where, we may not know where different vehicles are. So asset and ID tracking can help with preventing loss or having someone go and find out where this mobile platform is. It's going to reduce cost and maybe time of audits if people are coming through and auditing the plant. You can improve cycle time and plant efficiency by knowing exactly where each vehicle's at. It can help the enterprise system move vehicles from A to B more effectively. Secondly, you can work with fleet management. So if you know that, as an example, batteries are going to wear out and die and need to be charged, you can get indications from these connected devices on the performance of the battery, and say vehicle 3 needs to be charged. Let's have another vehicle go pick up where that vehicle left off and charge vehicle 3 while vehicle 5 is now taking over. So just one example of how you can manage the fleet a little bit more effectively with connected devices. Finally, we're going to shift to the total cost of ownership. To do this, we have to consider the entire life cycle of the machine. This will include everything from planning and engineering to the OEM selling the machine to the end user doing troubleshooting and maintenance on a mobile platform itself. So I like this graphic because it breaks down that machine life cycle pretty effectively. So if we start with the planning and engineering of the machine, this is where the bulk of the risk assessment and safety concept that Chris talked about comes into play. Based on the design of the machine, the size of the vehicle may dictate what size safety product could be used. So this may lead into using a smaller product such as the ScanGrid 2. You can see in the lower left corner of the screen, very small, compact device that isn't going to impact the overall size of the vehicle. So when you're designing the vehicle, you can make sure that it's smaller, you're not using as many resources or as much material to build it. So you're going to save the costs of that. Next, you'll want to look at electrical requirements. So these electrical requirements may determine what cabling is needed. In many cases, standard M12 cabling is used, and generally M12 cabling is very inexpensive and easy to find. It's generally sitting on a shelf or easily available. And then we look at stopping time. So stopping time is influenced by the velocity and load size, among other features of the vehicle. like Chris mentioned, braking capabilities is a requirement as well. The result of the stopping time helps determine the size of the protective field that may be needed within an optical device. So for longer stopping times or larger stopping times, a microscan 3 may be applicable. Microscan has fields up to 9 meters, which would help a vehicle moving extremely fast or with a very heavy load to stop in an effective time. Whereas for shorter stopping times, maybe that scan grid may be a good option because of the protective fields going out to about 1.1 meters. So depending on that stopping time, you may need a different device to handle those requirements. Moving to the purchasing of components, this is generally the next stage of the machine life cycle. This is the phase when cost is most transparent to the OEM, especially because you're spending money on something more tangible than labor or other factors that go into designing and building a machine. So the cost of components differs. It can range anywhere from low cost, low feature devices like a ScanGrid 2 to higher cost, high feature devices like a microscan 3. So this is, again, where it's tangible, and this is where costs are most relevant for people, but very, very small very small portion of this machine life cycle. So moving to the sale of the vehicle, this is the next stage of the general machine life cycle. Selling the machine is the time when the OEM actually makes money. So you need to make money somehow. Ultimate goal is to provide the best value and tangible benefits to your customer, which hopefully, if you sell the benefits and value effectively, the ROI from all of the components and the building costs of a platform will be minimized. And the big thing here is that if we look at that Goldilocks principle, if the solution is just right, it's going to prevent over-engineering and higher costs, and your customers are going to like that more. So the just right solution will prevent that overpricing due to over-engineering and the extra time that goes into developing that. And it also achieves that level of safe productivity that finds the balance between making sure you're still running effectively and hitting that performance level required and reducing the risk to that acceptable level. The next stage is the assembly. So generally, an OEM will make to order. It's not going to have. They're not going to have many devices sitting or many vehicles sitting on a shelf necessarily. So in a made to order scenario, assembling the machine comes next, and the costs associated are generally with labor involved. So for example, how much time does it take for someone to mount a safety laser scanner, or how long does the electrician need to route the cables and land I/O within the control panel? So making the assembly and configuration process as streamlined as possible will minimize costs associated. From a mounting standpoint, the ScanGrid 2 is designed for small mobile vehicles and has the potential to be mounted directly to the machine. This eliminates the cost of brackets and minimizes the assembly time needed. Next stage of the machine lifecycle is commissioning. Once the products are mounted and wired, we look to commissioning a machine. What this means is looking at configuration, testing and verification, and validation. The amount of time it takes the software engineer to configure the devices and integrate into vehicle operation systems is a labor cost that could very easily add up if the previous stages aren't done effectively. The ScanGrid, as an example, offers a configuration cloning tool that will allow the software engineer to minimize the time it takes to commission every single vehicle. So if you look at fleet deployment and a lot of these mobile platforms running around, it's very rare that you get just one vehicle that needs commissioning and rollout. So being able to configure all of these effectively is going to be critical. So that software engineer can minimize the time doing that with the ScanGrid as an example, because once that initial configuration is complete, you can actually use NFC technology built in to pull the configuration from that initial device and then wirelessly send it via NFC technology to subsequent devices. So instead of having to have a computer running around to different vehicles, connect to each one, configure each one, it's as simple as a tap of a mobile phone, for example. Next, we want to look at startup testing and validation. It can be a very labor-intensive process if it's not scaled and documented effectively in previous steps. So making sure the risk assessment is done correctly will simplify the verification and validation process and save time for any missteps that may occur along the way. Next, we look at operation. So once the handoff to the end user is complete, the machine now goes to operation. These costs now, as part of this total cost of ownership, shifts to the end user. If the machine is built to scale and the scale is just right, the operating cost should be at a minimum. We achieve that safe productivity for that end user to use effectively. This is where that safe productivity really shines. Next is troubleshooting. So end users also take on the troubleshooting costs. Troubleshooting historically requires on-site diagnostics, which are typically LEDs or error codes provided directly on the device. The product displays, many products have bright product displays, for example, on the MicroScan 3, that can provide a very clear guide to tell you what is happening on the vehicle. If, for example, the front screen is dirty, you will see an icon that tells the user the screen needs to be cleaned soon, which can minimize downtime in the near future. And we'll explain that from a maintenance standpoint. If a connected system is used, so we talked about connectivity and asset tracking and fleet management before. If a connected system is used, remote troubleshooting is enabled. The user can determine the correct course of action without even being on site. So this is all based on something as intuitive as an application-specific text message being received by a maintenance person. So both on-site and remote troubleshooting features will minimize the cost of time that a resource may otherwise need to put into the task. And then maintenance will eventually be required and is always labor intensive. That's a given. End users see costs in multiple ways with different maintenance. This comes with downtime or efficiency loss, resource or bandwidth limitations. Maybe someone's not available to run over to fix a vehicle at that moment. You could have material shortages, or it could be even OEM service contracts. The cost is being paid for by an end user. So to minimize these costs, a few things should be considered. First, you want to look at preventative maintenance. A vehicle system, including safety devices, may be able to provide data that could signal maintenance situation before it actually happens. So for example, we used this example previously, but maybe a safety laser scanner has a front lens that's dirty. And the remedy to this is that someone needs to wipe the screen during the next scheduled downtime. So we can provide an error code or a warning signal even to tell a maintenance person that a screen is dirty and needs to be cleaned, but the vehicle can still run. What happens is that this maintenance person schedules a time when the vehicle is docked next, when there's no productivity happening, it's just recharging the battery, goes and wipes the front screen. So the result of this is that there's no efficiency loss and minimal labor costs needed to clear that warning. The next thing to consider is just the ease of access to information. So if information is available remotely, there may be an opportunity to provide maintenance remotely. So in an example of an error code that could be recoverable, you could potentially send a power cycle to the mobile platform to clear that error code. And then if on-site maintenance is required and a replacement device is needed, it cannot require a lot of time and effort. In this situation, an example of an easy replacement would be with a MicroScan 3 FE Pro device communicating with the FlexiSoft safety controller. In the example, if the scanner needs replacement because it had another fork truck running by and bumped it, or it gets damaged, the process would be as simple as disconnecting electrically, then mechanically, and then dropping in the new scanner, mechanically, electrically powering it back up, and the program would be dumped into the scanner. There's no other programming that's required. So with the products that you're going to choose to effectively scale up and safeguard a mobile platform, these all need to be considered. So in general, there's a lot to consider for the total cost of ownership. It's not just the sale of the machine. It's not just the purchasing of components. It's worth considering the time and effort and other things included with the entire machine life cycle. And so if we turn back to the Goldilocks principle, we try to find the safety solution that's just right. And again, the benefit is there isn't just one right answer. The main mindset quickly goes to what optical safety device is needed. So in the image here, depending on the scale and performance levels needed, a small scanner may be needed with low features, or you could need, for example, a microscan that is full featured and a little bit more effective in larger applications. But you do need to remember that other components may still be required. Scaling safety will also consider things like the safety controls, like FlexiSoft, safe encoders, or safe inductive switches to detect wheel position or speed of the vehicle. So any combination of these devices may contribute to providing safe productivity in a scalable manner. And so this was a lot of information. There's a lot of different ways you can go about approaching scalable safety. So SICK offers a good partnership. SICK is in terms of scalable safety provides a very complete portfolio, including the products, systems, and then services, which can be, like discussed earlier, can be general safety training, risk assessment training, and those turnkey solutions. To do this effectively, we also have to look at the globe. We live in a world that's shrinking quickly. With borders a thing of the past, there's a SICK resource that will be close to you. So SICK globally services 88 countries through 50 subsidiaries, consisting of various sales and service units, production centers, competency hubs, and development teams. And specific to the SICK safety services, there are over 250 field service engineers, over 100 certified safety specialists, and over 50 certified application specialists globally to assist in providing the most effective, scalable safety offering for your application. This is all based on local laws and local regulations. So Chris, I'm going to hand it back to you.
All right, thanks for that, Aaron. Let's do this real quick. So I know we're starting to run a little low on time. We just wanted to kind of summarize here with a short video, kind of putting together everything that Aaron and I went over together. So I'll just let this video run, and if we have time, we'll try to answer some questions after. So with that, sorry, we had planned for some question and then discussion.
Wow.
I know we're running a little short on time here, Alfredo. So I think probably at this point, I'm assuming would be a good place to wrap up, right?
Yeah. I love the video, by the way. It's wonderful, very nice video. It really shows different applications and different combinations of navigation and safety with the different types of products. Well, I saw you also already answered some of the questions we had. I have just a few questions, guys, if you have just 5 minutes, because we are quite in delay, but there are a few things maybe that could be interesting to understand. All the safety standards that you saw in the beginning, okay, they are not mandatory, if I'm not wrong. They are just some guidelines, no? They are not just a must.
Right. Those standards, they're not legally binding.
Okay. So, but of course, it would be good to comply with them. Otherwise, I mean, also, I think also for competitiveness reasons, if I had to choose a supplier that is complying with these safety standards or not, of course, I would choose the one that is complying with, regardless they are mandatory or not. Okay.
Absolutely.
There was one question. Let me just check about the call to action Q&A. Okay, from Thibault. Okay, Thibault from in France. That he explained that there was a problem with an operator, and they were rating the laser scanner as B, and he said that the laser scanner should be always D, but in this application that he explained us, that's the rating of the safety lasers scanners are related, as you said, because of the are rated B or D or whatever they are, because depending on the application. I mean, if you have a forklift that is driving with 1 ton at 2 meters per second, they should have some kind of laser that is D. If you have a small AGC who is driving slow with low risk, it should have something like a B or whatever it is regarding the assessment. Is it right or not?
Again, it goes back to picking what's right or what's easy. And not that one is right or wrong, but in the simplified approach, like what I'm showing on the screen here, you assess the risk you say that whatever it is, you say that it's moderate to high risk and you need performance level D. One approach is you apply the you apply that performance requirement to every single thing that you apply, and then you evaluate the risk out only once when you're done. I've even seen where people aren't even evaluating the risk out. The other approach then, sorry, I just exited by accident, was the iterative approach that we were talking about. So in this iterative approach, you apply iteratively the risk after each step. So in the example we showed, if I go to that slide here, give me 1 second to pull it up here. Right here, we said that if we look at just the example of the collision, if we take the simplified approach, everything has to be performance level D. That's one way to do it. It's a broad brush approach that is easy to implement, easy to justify, but may not be effective, efficient, cost-effective, or necessary. So the other approach then is to iteratively go through it, like we showed here, and look at each safety function individually. If we first limit the speed limiting function has to be at a performance level D, which we can do. And if we successfully implement that safety function, then we are affecting the residual risk. We've reduced the severity. And now with a reduced severity, we then look at the next measure. Now that the severity, because we have an active safety function that we've verified and validated, we have lower severity, still high frequency, low probability. Now we evaluate the requirements for the next layer of risk reduction. So here, if we do this correctly, if we have the speed limiting correctly applied, verified, and validated, our severity is now lower. So now the safety requirement we're putting on the sensor has a lower level of performance requirement. And we can exceed that requirement through any of the ways that Aaron showed us. So the easy approach is you broad brush and say everything's PLD, go do it. It's easy to do in terms of finding off-the-shelf components, maybe not so easy in the verification validation, nor is it necessarily cost-effective, efficient, or necessarily required, versus if you take the extra time to do the iterative risk assessment, you can more granularly look at each layer of risk reduction, each individual safety function, to determine what is the actual requirement for each of them.
But case, even if you have a PLD, at the end of the day, it will also depend on how do you install these vehicles, because if you have a PLD that the safety scanner is working well with the PLD, but if you don't program properly your safety areas, maybe you have a problem there. If you don't have some kind of limit control or whatever it is. Is that right?
Right. Absolutely. I mean, it's not a simple approach that we can explain in 25 minutes. This check mark right here has days and days of discussion behind it. How do you verify and validate that you met a certain performance level? All we're saying here is it greater than what was required? But everything that goes into that simple check mark, that yes, you selected the components correctly, yes, you integrated them correctly, you applied the right diagnostics, the right fault exclusions, all the other things that go into achieving that performance level, and then checking to make sure that they meet the requirement. There's a lot that goes into that. But yes, that is one of the assumptions here, is that you're taking a more detailed approach, a more granular approach, but in the long run, you're coming up with a scalable solution that is in that Goldilocks zone of what's just right, instead of over designing everything just because it's easier, because it's not always easier. It's easier to justify. It's not always easy to accomplish.
And this comes to my next question that I saw that you already answered, but I think it's important for everybody, because I think this is quite complex, this kind of risk assessment and all the things that are involved. In fact, you have read 200 field engineers, 100 certified safety engineers, 50 application engineers. So you are also providing this kind of services in terms of consultancy, in terms of help for the risk assessment. But one question is, you do it for the machine, for the vehicle design, or also for the application or the installation in the factories or warehouse or in the application itself?
Yeah, we can support anywhere in the life cycle of the machine. We help OEMs with the design of safe equipment. We can help integrators with the safe deployment of equipment, and we can help end users as well with the machine as it's being used in the custom application specific deployment.
Okay, and another question, I put it in a general way. You saw now three safety scanners, okay, with different PL levels. Do you have other kind of sensors that are also PLD and are not scanners? I mean, sonars, radars, or other stuff?
So we do have a safe radar system that's been used in conjunction with various mobile platform applications. So it's not necessarily a product for use on these mobile platforms themselves, but I've seen them being used in conjunction in the general application. So I think I'll probably do your question before about the general application and where SICK can support. These products can go in the application. Even in the video, you saw like a safety laser scanner at the drop-off point of palletizer. So the vehicle is dropping off a load of pallets. We can use our safe radar system in a similar type of application to allow vehicle movement in and out effectively. But I think in the scope of that specific question, detecting the end of the forks wouldn't be a product directly on the forks at this point. We could look at a combination of products, safety radar, that's our safe RS system, or some safety laser scanners and figure out how to make that work. But it's kind of a yes and no answer to that question.
Okay, no worry. And I just placed the last question, and is this regarding the outdoor applications, okay? Is there some standard that is focused or specific for outdoor applications, or we just follow the ANSI area 58 or the 3691? And I'm asking this because I'm thinking about, for example, in outdoor applications, how do we do the risk assessment maybe for wet floor, or how can I set the laser scanner area? What conditions do I have to take into consideration for wet floor or icy floor? How do we do this?
Well, I guess there's a couple of questions in there. First, for the applicable standards, right? This product, and Aaron, you'll correct me if I'm wrong, it's designed to 13849. It's designed to 61496, Part 1 and Part 3 for an AOPDDR for an area scanner. We are also using a new standard, IEC 62998, for safety-related sensors and sensor systems to explain and justify how the technology can be used in non-traditional environments like outdoor or semi-outdoor. When we talk about the application standards, our 1508 talks about use of industrial mobile robots in structured or semi-structured environments. So just like this picture shows on the screen, if it's going between buildings, you still need to have worker safety here, right? And we need to make sure that we have technology and sensors that will perform as required in those environments. So as part of the risk assessment, you need to identify what those operating conditions are and make sure that the sensor selected or the sensor system that's created is going to maintain functionality throughout that use case. In terms of programming the field, it's very similar. It's identical to the way you would program the field on an indoor application. It's a function of the speed of the mobile platform and its stopping capability. It's a function of the approach speed of the first case. You have a mobile platform and a person coming towards each other, and you need to be able to account for the speed differential. You need to account for the braking capability and set your field size accordingly.
At the end of the day, in each application, there is a kind of trade-off between the customer safety regulations, internal regulations, and the project itself. For example, if we think about towing tractors, okay, that you have the safety scanner in the front of the tow tractors, and you don't have any kind of protection between the trolleys, okay. It's true that there's always a risk there between two trolleys or in another conditions, and sometimes, as Aaron was saying before, it is not worthy or is not possible to just put in safe conditions all of these trolleys, because maybe they hook, and then there is assessment is maybe it's about training or warning lights or other things, So I've seen that at the end of the day, there is for sure there is the machine, the application, but there is also to see what is the customer thinking, or what is the reasonable risk that the customer could afford. It could change depending on the customer. Do you see also this in your market, in your applications?
Absolutely. I mean, like this slide shows, there's a minimum mandatory safety functions. There's a number of other optional ones depending on the application. Maybe when there's muting of the safety function, that has to be under certain safe conditions. You have warning systems or other layers of risk reduction in place when that sensor is not active or muted. It goes back to the idea of the risk assessment process in general, where you often people would stop at step 2, say, okay, I'm at the performance level, I'm done, and not consider, are there other measures either required by standards, by regulation, or simply to reduce the risk to that ALARP concept as low as reasonably practicable? Is it addition of signs and documentation and training and supervision, all those things that are admittedly harder for the supplier to implement, but definitely important for the end user to make sure those extra levels of risk reduction are in place, right? If I design a system under certain conditions and think it's only going to be used where there's trained individuals, and then somebody takes that industrial device and lets it loose in an airport or a grocery store where you have soccer moms and kids and elderly people that don't have the mobility, that don't have the level of awareness or the simple understanding, then you're going to have a mismatch where your risk assessment didn't actually match the deployed operating environment, and you're going to have solutions that are hard to get you to that level of acceptable residual risk.
Yeah. I had an application. What you are saying is exactly what I saw, because we were applying the typical procedure that we are doing for the risk assessment and the risk procedure in that project, but we had a problem because in that factory there were a lot of visits from external people for watching the factory and watching. So we had to put barriers everywhere that otherwise maybe we could not do it, because we could not train everybody that would go into the factory, not to go into the path or to when it's going. There were many things. So it depends also, as I said, in the application of each who is using these machines and what is the environment. So at the end, it's a trade-off of many things, I think.
Right. Yeah, typically, there's no silver bullet. There's not one thing that's going to make the machine magically safe. It's layers and layers of measures, design measures, engineered measures, and administrative measures that are going to reduce that risk as low as possible. It goes back to the discussion we had early on that acceptable residual risk is still somewhat subjective, and it is based on the environment and the exposed people. We need to reduce it as much as possible to that realm of acceptable. And it's not just what's legally required, it's also what's state of the art that can get us there, but what's as low as reasonably practicable. Is it practicable to put a sensor on it and say that we're done? Or do we still need to train? Do we still need to provide PPE? Do we still need to make sure that there aren't random people walking in off the sidewalk, walking around our warehouses and factories where they could be exposed to risk? There's many, many things that go into a cohesive risk reduction strategy.
Yeah, imagine a hospital, for example.
Absolutely.
Okay, well, I think we have seen everything, I guess, I mean, something about safety, because everything today would be quite ambitious. And we will send you an email, of course. Thank you, everybody, because again, we've been some hundreds of people, and we wait again. We'll send you an email about with the contacts of Chris, Aaron, and network. Whenever you have questions, feel free to contact us. The presentation, you can always see the downloadable PDF that we saw in the risky iteration process that Chris was showing. We will provide an on-demand webinar afterwards. It will take some time because video is quite new and is still under development. But after some days or a week more or less, we will have this on-demand video, on-demand webinar available, and we will also send you a link. So Aaron, Chris, thank you very much for your time and for this explanation, and it's been very, very useful, and I've learned a lot. I don't know, I hope everybody learned something, but for me it was very, very, very nice. Thank you, guys.
Thank you. Take care, everyone.
Thank you very much.
Bye-bye. Bye, everybody. Thank you all. Thank you.